we're making is, first of all, we're seeing the volume of the gas is way larger than the volume of the liquid or solid. So the change of volume is basically the change of your gas volume. Then we assume all gases are behave ideally. So we can use our ideal gas law. And then we make the assumption that delta H has remained constant along the equilibrium line. So that's why we can take the delta H outside from the integral to get to this final expression. Right. So with this simplified Clapeyron equation in hand, we went over doing one problem together, which is this problem, like how do we set up the calculation? I recommend like just basically graph your PT diagram and put whatever you know on that diagram so you have an idea about what exactly is the problem we're trying to solve. And let's look at another practice problem here. So this is the same kind of problem, but instead of giving you what are the pressure and temperature at your point 1, this one asks you to use the data in table 7.1 to estimate the boiling point of argon at 1.5 atm. So what we have in this question. Again, the first thing is we want to set up our problem, right? So if we write our diagram here, we have pressure, we have temperature. So some of the things we know, for example, by reading the table, let's find argon first. That's too big. Okay, so let's find argon. Now, one of the things we know in the table is our normal boiling point temperature and also the vaporization delta H. Right, so what we know is we already know what is a normal boiling point. So we can put our normal boiling point, so T, normal boiling point, and also the corresponding pressure is normal boiling point, so we know this is 1 atm. Right, so what we are trying to solve is at a higher pressure, like 1.5 atm, we're trying to solve this new boiling point. All right. So some of the additional question you can think about is when we're having this kind of diagram on your PT diagram, just think about why this one is why this slope is like a positive slope. So that's a qualitative picture of the phase diagram. If you don't know the answer, go back to the phase diagram and review it a little bit. Now we're at this problem that's being defined. We know 3 here, and we know like 1.5 atm. And what we need to do is to use what we have in the table to solve for this new temperature. So the equation we're using is your simplified version of your logarithm P2 over P1, roughly equals to negative delta H molar enthalpy over R. That's 1 over T2 minus 1 over T1. So in this case, since our temperature change or the pressure change is relatively mild, we can assume your delta HM is constant. So again, that's one of the approximation we're using. And what are the things we know? Now, in this case, our P1 equals to 1 atm. Our P2 equals to 1.5 atm. The delta HM is this one, 6.53 kilojoule per mole. Your R is a constant, so 8.314 joule per mole per Kelvin, and you need to keep in mind the unit difference. And then in here, your T2 is something we're trying to solve for, and T1 we know that it is our normal boiling point, which is 87.3 Kelvin. So we have everything ready to solve for T2 in this case. All right, and I trust you can use the calculator to finish that calculation. So this is why I think it's a very good idea you put everything in that diagram so that you know what are the things I know, what are the things I don't know, what exactly I'm solving for. It doesn't take you more than 10 seconds to do that. All right, any questions on this one? No? Okay. Next up is our solid-liquid equilibrium. So again, the solid-liquid equilibrium, we start from the general form of the Clapeyron equation, which is this differential equation, right? We're talking about the differential of dP over dt equals to delta Hm, T delta Vm. Now, we're gonna use a little bit more approximation to try to come up with an easier to use liquid to solid equilibrium equation. So what we have here, the first step after rewrite it is always integration. Right, so integration on both ends, we end up getting dP equals to T1 to T2 delta fusion H over delta fusion V times T and dt. Or since we're talking about the delta fusion H over T at constant pressure, which is where your fusion takes place, this actually equals to T1, T2, delta fusion of S over delta fusion of V dt. So the approximation we're making here is that if our pressure change is relatively small, so when we say it's relatively small, as long as your pressure change is not like above 1,000 atm, it's considered pretty small. So we can assume our delta fusion S, delta fusion H, and delta fusion V are constants. So this approximation is very straightforward. We're just saying, like, as long as you see that pressure change is not extremely big, you can just use this number from that table to do the calculation. And that largely simplifies this model to my P2 minus P1, or the changing pressure, equals to, or relatively equals to, the delta fusion S, delta fusion V, and T2 minus T1. Or this one relatively equals to delta fusion H over delta fusion V logarithm of T2 over T1. All right, so the reason between these temperature is in this original equation, you have temperature below, so you have to take that into consideration when you do the integral. But here, our temperature basically embedded in entropy, so it doesn't appear anymore. So very straightforward. Just know whenever the pressure change is not too big, you can just use one of these equations and find what are the things you know and how to use it to solve for the problem. Okay. So we'll do one more example problem on the Clapeyron equation, and then we'll start our review on chapter 7 and chapter 6. So here's the problem. I'm gonna read it with you and ask you to do it for a little bit of the time, and then I'm gonna do it on the board. So what we have, the vapor pressure of sulfur dioxide solid is 1.0 torr, at 177.0 Kelvin and 10.0 torr at 195.8 Kelvin. The vapor pressure of the sulfur dioxide liquid is given, and then ask you to find the temperature and pressure of the sulfur dioxide triple points. And then with that information, you can also find the delta H of the fusion of the SO2 at the triple point. So let's focus on the first problem here, because once you know the temperature and pressure of the triple point, calculating the delta HM will be more straightforward. So I'll give you 5 minutes to set up the problem, and then we'll do it together on the board. are we doing? So what I was doing is basically copy what's in the question onto a phase diagram, right? If you look at what we put is, well, it gives you a field combination of your temperature and pressure, right? So for the solid, you have the 1 torr and 177 Kelvin. You have the 10 torr and the 195.8 Kelvin. Now this line here gives you the equilibrium line between your solid and your gas phase. So we can use this equation, but we're talking about the delta HM. You can find that number in the table for the solid gas equilibrium. Now, the other 2 points we have are here, right? So you're reading it. That's the vapor pressure for the liquid sulfur dioxide. That's 33.4 torr and then 209.6 Kelvin, and 100 torr and 225.3 Kelvin. So it's also nice to write down what are the phases on top and below that curve. Now, that's everything we have in the problem. And we look at the question, find the temperature and pressure of sulfur dioxide at the triple point. So we know that at the triple point, there must exist some kind of line between your liquid and solid. And also your solid and gas are in equilibrium, your liquid and gas are in equilibrium. All right. You can also try solve it using that liquid gas line. It's just like much harder comparing to what we have. Because here we can use this equation again. So that's the setup of the problem. Now, how do we actually solve it? So if we look at it, we have the solid phase, solid gas equilibrium. So we look at it, we have the logarithm of P2 over P1 roughly equals to negative delta sublimation HM over R 1 over T2 minus 1 over T1. All right, so next step is just plugging numbers. Well, in this case, we have P2 equals to, well, let's say that's my P2, T2, that's my P1, T1. So we're just plugging numbers. So 10 over 1 roughly equals to negative delta sublimation HM over 8.314 1 over T2, 195.8 minus 1 over 177. You can plug that into your calculator. That gives us, well, I'm actually going to plug it with you. So your delta H of sublimation is about 35290 joule per mole. And then what we have is then with that delta H sublimation in hand, we can use this relationship to try to set up an equation that contains both P triple and T triple. So this one we're using our delta sublimation. Right, so we're still aligned along the solid and gas solid and gas line, so we can use that number. So that gives us our first relationship. That's ln P triple over 10. I want to maintain my pressure difference as small as possible, so I choose that 10 instead of 1 to do this calculation. That's roughly equals to the negative 35290 over R, which is 8.314, times 1 over T triple minus 1 over 195.8 Kelvin. But now we still do not have enough information to solve this equation. We have two unknowns. We only have one equation. So naturally, you could expect we use the same kind of logic to work out a liquid-gas equilibrium and use that to set up my second part of the calculation. So that goes to my liquid-gas equilibrium. Right, so the idea is the same. We first use this equation to solve for the delta vaporization of the vaporization enthalpy. So 100 over 33.4 roughly equals to negative delta vaporization of enthalpy over your gas constant times 1 over 225.3 minus 1 over 209.6. All right. And then once you solved for the delta vaporization of HM, you can do the same thing. You plug it back into this equation and get another type of this equation that represents your triple point pressure and your triple point temperature. And with those two equations together, you can solve for the triple point temperature and pressure. Okay? So this is one of the questions that it reads very short, but if you actually have to do it stepwise, it's going to take you a lot of time. So know what to expect and know how to set up the problem. So once you draw the figure, then it becomes quite obvious what are the steps we're taking to solve this problem. All right. Any questions? No? Okay. All right. Next up, we only have 20 minutes, so I'm gonna just jump into our review on all the topic we went over after our midterm 2. So that's everything after midterm 2 until today, and what we covered, and that's gonna be about 25% on your final exam. So all the way until the midterm 2, we were talking about, okay, what are the definition of those thermodynamic properties, how to construct a thermodynamic table, and how to calculate those thermodynamic properties or state functions like delta H, delta S, delta G for a reaction, etc. So chapter 6 is where we actually make a link between these state functions to something like chemically meaningful to us, like what is the composition at equilibrium for a specific chemical reaction or for a mixing process. So chapter 6 is building that connection between equilibrium constant and also the thermodynamic properties. So we start by talking about chemical potential in an ideal gas mixture. We did a few steps of derivation to get to this one important equation for ideal gas mixture. So the take-home message here, So the take-home message here is do review and make sure you know how it's being derived. So some of the things we used in this process, including, for example, we have a pure ideal gas. That means like for a pure substance, the chemical potential equals to the molar Gibbs free energy, and you can use the Gibbs equation for that Gibbs free energy. Right, and at the same time, when we're talking about ideal gas, we have PV equals nRT. All right, so that's the first thing. And we did an example together, which is problem 6.1, in how to apply this equation to do some mass calculations. Then we went over a chemical potential of, I think I'm opening the wrong note, sorry. Okay, this one is more correct. All right, and then we went over, talking about chemical potential of the gas I in an ideal gas mixture at certain temperature and partial pressure. So now know what these terms mean. Like this PI means the partial pressure of a specific substance. The stars denotes for that is a pure substance. And in this problem, let's do some true and false together really quick. The first thing, the chemical potential of an ideal gas I in an ideal gas mixture at temperature T and partial pressure PI equals to the chemical potential of pure gas at temperature T and pressure PI. So this one is true because we don't care about what exactly is, whether or not that pressure is in a mixture or as itself, right? So your chemical potential just equals to, because we're assuming it's ideal gases, so you have the PI just equals to chi I times entire P. So we don't really care about what your total pressure is or whether or not this gas is in a mixture or not. The chemical potential is the same. Next up, we have mu of a pure gas goes to negative infinity as P goes to infinity, and chemical potential goes to infinity as P goes to infinity. This is what you see on your midterm 2, This is what you see on your midterm 2 exam, yes. And the idea behind it is we have this curve, right? So on the y-axis, you have mu minus mu naught. On the x-axis, you have a pressure, and it's a logarithm function, right? So it's basically just going all the way up. Then we look at C. The entropy of a mixture of N2 and O2 gas, assuming they're ideal, is equal to the sum of the entropies of the pure gas, each at the same temperature and volume as the mixture. So this one is something that's obviously wrong because we did a lot of time talking about the entropy change for mixing of ideal gases. All right, so we did that delta S mix equals to, well, you have different versions to write it. One of it is Na number of mole of your species A minus Nb R ln chi B. Now, without writing out that equation, you could also think about why it is true. Because during the process of mixing, it is like an irreversible process. Your entropy is changing in the process, so it can't be the same. All right, just a quick refreshment on how to do your multiple choice, your true and false problems. So again, these true and false problems, they're not hard, but they constantly jump back and forth between different concepts on different chapters. So do practice on those chapter end problems, especially focusing on true and false problems, so you're familiar with it. Next, we went over the ideal gas reaction equilibrium. So that means we start by a few derivations to go to the definition of our standard equilibrium constant, and also the relationship between your standard equilibrium constant to the standard Gibbs free energy. And then we went over how to use what we just derived, the definition of equilibrium constant and delta G of the reaction to actually solve for equilibrium composition. So this is the example we did in class, right? It gives you initial number of mole of your reactant, gives you the volume of the container, gives you the temperature and the pressure at equilibrium, and ask you to find equilibrium constant at that specific temperature. So a few steps we did to solve this problem. First thing is we solve for the total number of gases at equilibrium, right? So that you can do by using the ideal gas law. And then express that total number of gas in forms of extent of reaction. So you can solve for extent of reaction, or extent of reaction C just tells you how many more of reaction that's been taking place. And then with that in hand, you can solve for equilibrium constant and then vice versa, the delta G of the reaction. It's always a nice sanity check for this kind of problem because you can calculate delta G using the thermodynamic table. So that can always gives you a sanity check in whether or not I get the number correct. Okay. There are different versions of equilibrium constant. We did not go into very much detail because they are pretty straightforward to interconvert between these different versions of equilibrium constant. So for example, if we start from the pressure version that uses partial pressure and the standard pressure, since we have for ideal gases, your pressure just equals to the concentration times RT. So concentration is defined as number of mole over volume. So that gives you the concentration version of the equilibrium constant. So since the transformation is relatively straightforward, just know how that's being done. You might have one or two multiple choice on this topic, but not too much. And yeah, the chapter end problem is actually pretty nice organized if you haven't seen it. It tells you which subsection those problems are for. So when you're practicing it, you can just sort of go to the chapter end and find that specific subsection you want to practice on. 6.3, we went over the Van 't Hoff equation. How do we derive the Van 't Hoff equation, and how to use the Van 't Hoff equation to solve the equilibrium constant. Well, to link the equilibrium constant and also the heat of the reaction. So one of the things I want to quickly emphasize again is, well, that's the original form of the Van 't Hoff equation. But when we plot it, we typically plot the logarithm of your equilibrium constant, which is fine, as we expected. But on the x-axis, we typically plot it as 1 over t. All right, so know why we're doing that. So for example, in this case, why we're plotting the logarithm of your equilibrium constant, which is here, not over t directly, but over 1 over t. So the reason behind is you have the differential of 1 over t over dt equals to negative 1 over t squared. So dt equals to negative t squared differential of 1 over t. So if we put this one inside here, what we end up getting is a differential of logarithm kp naught over negative t squared d 1 over t equals to delta h naught rt squared. And your t squared will cancel out, so it gives you a much straightforward expression. So d ln kp naught d 1 over t equals to negative delta h naught over r. So the physical meaning of this differential is the slope of this curve here. All right, so you might have a question ask you to quickly illustrate what's the physical meaning of the slope below this curve. And then we went on and talked about how to use the Van 't Hoff equation for ideal gas reactions. So in this process, we again just did start from the original Van 't Hoff equation that doesn't have too much approximation in there. But when we're using it, we added a little bit of the approximation. So in this case, when we're doing the integration, we approximate that your delta H naught is constant when your change of temperature is not too big. So we see the change of temperature is not too big. Let's just say it's like within 200, 300 Kelvin. And then you can approximate your Van 't Hoff equation into some kind of form that's easier to use. It's the same kind of logic when we're working on the Clapeyron equation. The original form of the Clapeyron equation, which is a differential equation, is quite accurate. But when you're actually using that equation in a specific setup, then there are approximations for using. All right, so one of the questions you could think about, now, instead of assuming my delta H naught is constant, we tell you that your delta H naught, for example, equals to AT squared plus BT, and how to use this expression to get a more accurate representation of your equilibrium constant. All right, so this is the original form of your Van 't Hoff equation. But in specific setup, when we tell you more information about delta H naught, then things might be different. So your textbook has a pretty good example, just ask you to use the Van 't Hoff equation to solve for temperature change for different ranges, and you'll see that this approximation might fail when you have like too big of a temperature difference. All right. Next up, we have the ideal gas equilibrium calculation. So this part is more like a elaborated GenChem kind of calculation, right? We're using these two fundamental equations, your delta G equals to negative RT ln Kp, and your standard equilibrium constant is defined as following. So this part is more like a elaborated GenChem type of calculation. So we did this example together in class, following the 6th step to solve for the equilibrium composition. So if you don't remember how to do it or how to approach this problem, we're going to quickly go over the setup again and just refresh your memory on how to do that. You have plenty of practice problems like that in the textbook. Now, the first step is to calculate our delta G of the reaction. So you can find that using our thermodynamic table. Use your delta G naught, the Gibbs free energy of the reaction we calculated, to translate that into the equilibrium constant Kp naught. Now, with equilibrium constant Kp naught, you might, it depends on the actual question. Now, once you have the standard equilibrium constant, we might ask you to solve for the equilibrium constant at a different temperature. And that's when you use the Van 't Hoff's equation. All right, so it depends on the temperature we're asking for. You may or may not need to use the Van 't Hoff equation. And then express your equilibrium constant in either Mohr number or partial pressure. But basically, we're trying to set up an equation that's dependent on the extent of the reaction. And using the achieved equilibrium constant, we can solve for that extent of reaction C. And once we have the extent of reaction, well, you can calculate what's the equilibrium composition that exists in your reaction mixture. So this part it's going to be really like calculation heavy. You could easily imagine this one to be one of your comprehensive problems. All right. And then 6.6, this part is more qualitative. Like before we were talking about the quantitative picture, we're actually calculating equilibrium composition. This part is more qualitative. We're talking about like, okay, without doing too much calculation, can you just quickly tell me where my equilibrium is going to shift? So this part is like, for a chemist, it's very useful to know, like, or for a biochemist, it's very useful to know, like, when you have increased pressure, increased temperature, how your equilibrium is going to shift, or when you add like reactant, when you add product, how your equilibrium is going to shift. So the fundamental idea here is we're comparing what we call a reaction quotient with an equilibrium constant. So know that here the equilibrium constant is a different version. So before we have the standard equilibrium constant. So you have the partial pressure divided by the standard pressure. So that cancels out the unit. But when we're comparing equilibrium reaction quotient, we're comparing it with the equilibrium constant. I know the naming is really, really confusing, but this one just not the standard equilibrium constant. This one is the equilibrium constant, not the standard one. All right. So you're comparing the value between these two values. Whether when your reaction quotient is smaller than your equilibrium constant, you have forward reaction, or your extent of reaction is positive. When these two are equal to each other, your extent of reaction is 0, means it's at equilibrium. Your reaction is not going anywhere. And when you have reaction quotient larger than equilibrium constant, that's a backward reaction, and your extent of reaction is negative. So these parts are some of the mental gymnastic you have to do to make that link. But if you don't know how to do that, just review that chapter a little bit more. And then we have 6.48 that I don't think we have went over. Okay. So I have all the workout for it, but then we didn't actually go over it in class because we were running out of time. So let me do that today, because I don't think I want to spend too much time reviewing our chapter 7. It's still pretty fresh. So this one, let's do that together. Now, the first question, the question gives you an ideal gas reaction where you start from PCl5 gas, goes to PCl3 gas, and Cl2 gas. So start from one gas, goes to two gas molecules. And ask you to tell whether the equilibrium shifts to the right, left, or not going anywhere. So you can use the appendix data. First problem, we have the temperature as decrease at constant P, or you can write it as an isobaric temperature decrease. So temperature is changing, so my equilibrium constant is changing, but my composition is not, so my reaction quotient is not changing. So that, again, goes back to my definition here. So this only cares about PI. So your partial pressure is not changing because we're only changing the temperature, right? So your Q is not changing, but the equilibrium position might be changing. So in this case, my Q is not changing. And what we have for equilibrium constant, so this gives you, well, or use our Van 't Hoff's equation. You have dkp over dt equals to kp naught delta H naught RT squared. Or our take-home message is that the change of your kp naught has the same sign as your delta H naught. So this delta H you can get by the thermodynamic table. And in this case, I'm going to tell you our delta H is positive. Now, what that means is this one is an endothermic reaction. Your dkp naught over dt is positive. So that means when we have temperature decrease, my kp naught is also going to decrease. So with your reaction quotient not changing, your equilibrium constant decreased, so your Q will be larger than your kp naught. And that means we have a backward reaction. Right. Next one, we have the isothermal volume decrease. So isothermal, whenever you see an isothermal process, that tells you your kp naught is not changing. So your equilibrium constant is not changing. But since we have a volume decrease, what that means is your partial pressure equals to Ni RT over V. Now, everything else is not changing, but your volume is decreasing, so all your partial pressure will increase with your volume decrease. All right, so your QP equals to the product of all your partial pressure to its stoichiometric number. So that boils down to how many number of gas molecules we have in our reactant or product, because the partial pressure of these gases are more sensitive to the volume change. So in this case, our reactant has only one gas, our product has two gas. So that means our QP is gonna increase. All right, so all your PI is going to increase. Your partial pressure is going to increase. Just depends on how many gas molecules you have in the stoichiometric relations. So your QP is increasing, so QP larger than K. So again, this one is a backwards reaction. So these kind of problems are more likely to be either a multiple choice problem or a short answer problem, like just a quick answer, like just quickly derive what do you predict. And then you can have remove of your reactant. So again, constant T tells you my Kp is unchanged. So my partial pressure equals to, again, Ni RT over V. So all the other reactant or species are not changing. So the partial pressure of your PCl3 and PCl2 are not changing. But the partial pressure of your PCl5 will decrease because we're removing PCl5 from your reaction mixture. So what is our reaction quotient? So that's my PCl3 times the partial pressure of your Cl2 divided by P PCl5. So the top two are not changing, it's constant. The bottom one is decreasing, so your Q is increasing. So your QP is larger than your KP again. All right. And well, the rest is like adding inert gases, and basically tells you like, okay, so adding inert gas at your constant TV is not going to change anything because, well, your temperature is not changing, your KP is not changing. Adding inert gas to your ideal gas mixture doesn't change the partial pressure of your initial reactant or product, right? So your QP will stay equal to the KP. And then we have the addition of inert gas into a mixture where you have constant T and constant P. So here it's different because constant T and constant V or constant T and constant P. That tells you different information. So in this case, your KP is not changed, but the total volume will increase with the addition of helium. All right, so when the total volume increase, all your partial pressure will go down. So this gives you a forward reaction. So do that derivation and get it yourself. The rest of the review of chapter 7 is pretty straightforward. We only talk about three things in chapter 7. First, the degree of freedom, so the general phase rule. And then the one component phase diagram, know how to read it, how to get qualitative and quantitative interpretation of the one component phase diagram. And yeah, that's all. Okay, see you on Friday.